So I'm going to talk about accelerating software 2.0 and try and keep us on track so you guys don't get delayed too long for lunch. Thank you for inviting me to speak here. So let me start by saying there are kind of two big trends driving computing, right? So the one, of course, is the fact that Moore's law is slowing down, right? So Moore's law, of course, has been driving the industry for the last 50 years, and it's getting to the point where the time between process generations is getting longer, and the transistors that you can put on the chip aren't necessarily getting cheaper. But more importantly, the companion law, Dennard scaling, is over, right? Which means that if you want to increase the performance of your chip, you're going to burn more power. And so fundamentally, we need to come up with ways that are more energy and power efficient if we want to increase performance. And so that means conventional ways of designing systems with general purpose CPUs are not going to be things that power us going forward. The other big trend, of course, is the ascendance of machine learning, of course, and you guys don't need to belabor that point here because that's why we're all here, and that's why there's this huge excitement in what ML is able to provide on very tough problems that have to do with things that typically humans do, like image recognition and natural language understanding, and automating things in our life, such as driving cars and other sorts of things, right? So from a computational point of view, there's a sensational demand for training these machine learning models and for serving them to millions of people on the web. And so you have this point where you've got this declining capability from the underlying process technology and this huge demand for computer performance to train and infer machine learning models. And so fundamentally, this means we need a new approach to designing computer systems for ML to keep track. So the rise of machine learning and improvements in computational power have been intimately linked over the years, right? So neural networks have been around for a long time, 50 years or more. Actually training them with backprop has been around since the 1980s. And so, why did they become ascendant? Well, it was basically, if you look on the x-axis, you look at the data that we had to train these models, and the model complexity enabled them to reach much higher accuracies, right? So whether that the problem being solved was recognizing images or translating natural language, you got to the point where the models were complex and capable enough that they beat conventional hand-developed algorithms. And that, of course, was made possible by tremendously increased compute capability, which was predominantly provided by GPUs. And so this idea of training neural networks based on data instead of coming up with hand-curated algorithms has been dubbed by Andrej Karpathy, who I think gave a talk yesterday, as software 2.0. So I think this is a great way to describe what's going on. And software 2.0 means, of course, that this changes fundamentally what a lot of the software developers do is they focus their time on collecting data and building models rather than coming up with algorithms. And so the question then becomes sort of how do we accelerate software 2.0? How do we make it more possible to use these techniques across a broad area of the problems that we want to solve? And so fundamentally, this means we need more computation. We need 100 or 1,000x improvement. And as I said, given the fact that we are fundamentally power constrained, we need to do this in a more energy efficient way. We need to do it in a way that doesn't compromise the flexibility that we have with conventional CPU processors. So ultimately, we want to have performance that you might get from a fixed function ASIC, and also the flexibility that you typically get with a processor. So how are we going to achieve these two opposing goals? Well, we need a full stack integrated approach that looks at where the machine learning algorithms are going and how to come up with new ones that are better optimized for new architectures. We need ways of describing these algorithms and optimizing these algorithms with sophisticated compiler technology. And of course, we need new hardware architectures that are much more efficient and flexible in order to take advantage of these things. So for the rest of my talk, I'm going to talk about these three elements. So first, ML algorithm trends, right? The overwhelming trend, of course, is the increasing model complexity and size, which enables you to do more accurate, come up with more accurate models, right? So this is a good example of where this is taking place is in language translation models, right? So, Google came out with a paper that said, attention is all you need, and so people are building these larger and larger attention-based, transformer-based models, starting with, GP2, around sort of 3 million or so parameters, growing at a rate of roughly, doubling the number of parameters in the model every 3 months, right? So this is a tremendous rate, which of course is clearly outstripping Moore's law at its height, let alone when it slows down. And so what are people, what you can do, of course, is, by increasing the model size, you get increases in accuracy, and to, large internet companies, small increases in accuracy translates to millions of dollars, so they're very motivated to do this sort of thing. And so, NVIDIA came out with a paper saying that, hey, we could train a much more accurate model with 400 GPUs that had 1.8 billion parameters. However, if you looked at the efficiency of which those GPUs were being used, it was only 20% efficiency. And you needed 400 GPUs because, of course, the GPU memory is limited, and so in order to hold 1.8 billion parameters, you needed 400 GPUs to contain the model, right? And so Microsoft came up with a slightly more efficient way of doing this. And so they were able to get up to 17 billion parameters and increase the accuracy even more. But this, of course, took 1,000 GPUs. And you look at the efficiency with which those GPUs were being used, it was 6% efficiency. So if you look at the flops being delivered with 1,000 GPUs at 6% efficiency, there was actually less than the flops being delivered with 400 GPUs at 20% efficiency. So of course, this trend can't continue because sooner or later we'll have no flops being used at all. Right? So we need a better approach than this, right? So the other thing, one of the things that ML researchers are spending a lot of time looking at is sparsity, right? So how can you increase the size of the model without increasing the number of parameters by not making all the connections? And of course, if you look at a trained model, it is in fact sparse. And so the question is, can you train with sparsity? And people are starting to look at that. However, of course, the issue is that now you need a hardware accelerator that can deal with sparsity in an efficient way. And of course, most of the accelerators we have today are focused on dense matrix operations and don't do sparsity that well. Another idea that's driving sparsity is the use of graph neural networks to represent people, places, and things. Communication networks, again, if you can model the world in a more accurate way, then the machine learning model that you derive by doing this is going to be more accurate too. And again, the issue is GPUs, for example, are not that efficient at graphs processing because, again, graphs look like sparsity. So the benefit, of course, of the software 2.0 approach is that it is probably faster and easier to develop a new model than to develop new algorithms. And an example of this is, at Google, they translated their language. They transferred their language translation code from 500,000 lines of C code to 500 lines of TensorFlow code. So TensorFlow, of course, is Dataflow. And most of these models can be represented as the connection of multiple operators or kernels in a Dataflow fashion. And so that's the first point I'd like to make about these algorithms is they fundamentally are data flow. And the question then is sort of, how you take that data flow and optimize it to execute it efficiently. So we just had a talk about Keras and TensorFlow. And so these models are represented in both PyTorch and TensorFlow, which are domain-specific languages that allow you to represent the data flow. And so we've done a lot of work at Stanford in compiling these languages, and one of the conclusions was that you could represent this data flow efficiently using what we call parallel patterns. And so these are map, reduce, group by, and so on, filter. And the key to it is that you need to nest these patterns, so you need a hierarchical representation. But once you have this representation, then it becomes a substrate that you can use in your compiler to optimize both the parallelism and the memory characteristics of your algorithm so that you can get very good performance. So with these things in mind, I should mention that SQL can also be represented efficiently with parallel patterns. And I'll come back to this later in the talk. So then the question then is, right, so I've got these ML algorithms and I want to design an accelerator that can give me much better performance than conventional approaches. So what things should I consider? Well, one of the first things you consider is that the multi-processing approach or the multi-core approach, which is prevalent in general purpose processors and GPUs, the idea of connecting together multiple instruction set processes is basically running out of steam, right? The processes themselves are not efficient enough, and when you combine multiple of them together, you get even greater inefficiency. So we need an approach that is not necessarily processor core focused. Then the other trend to understand is that this notion of having accelerators for training, which are different from accelerators for inference, is starting to go away. In lots of cases, when you're doing inference, you might like to fine-tune the model, which means that you need some sort of training capability. There are some new ideas for developing models that instead of building one large complex model, you have lots of small models that are trained on the fly, right? So almost continuous training. And again, here you need training capability. And so if you can do inference and training efficiently on the same piece of hardware, then this gives you the benefit of being able to take advantage of these sorts of ML techniques. And lastly, the idea that you have an accelerator just for ML is something that is not necessarily going to be a winner in the data center. Ideally, you'd like to accelerate the whole data analytics pipeline from SQL to post-processing of your model, and this would allow you to keep the data in the same place, potentially, and of course have a much more widely applicable acceleration solution. And so with these things in mind, then, what do you want to support on your Software 2.0 accelerator, right? So I've argued that hierarchical parallel pattern data flow is this fundamental execution model that spans all of data analytics, and so you want to be able to support that efficiently. And of course, it provides a platform for future innovation, right? So if you've got something that has these components, then you can think of coming up with new ML algorithms that are based on this model. Sparsity is becoming an increasingly important area, right? So you want to be able to execute sparse models efficiently. And lastly, you want to be able to do flexible mapping of your models to your accelerator, right? So traditionally, on a GPU, you take one kernel at a time, and you accelerate it in a data parallel manner, right? What you'd like to be able to do is do that. In addition, you'd like to be able to take there you're kind of replicating the kernels or replicating the data flow graph. What you'd also like to be able to do is to take a single kernel or a single data flow graph and extract parallelism out of that. That is called model parallelism. And you'd like to do anything in between. You'd like to mix and match, right? So the more flexible you can be, the more efficient you can use your hardware. So you want that sort of capability. And so the approach that we've taken is this idea of what we call a reconfigurable data flow architecture. So there's a famous architect named Jim Smith. He was a professor at the University of Wisconsin, and he also was also a designer of Cray machines. And he said, if you have a vector problem, then you should build a vector computer, right? And so, we have a data flow problem, so we should build a data flow computer. And so the way that we build a data flow computer is one that matches our hierarchical parallel pattern representation of the algorithms. And it's a tile-based architecture composed of what we call pattern compute units and pattern memory units, which are designed to execute these parallel patterns efficiently. So let me take a small click into these key components, the pattern compute unit and the pattern memory unit. So the pattern compute unit is meant to execute these parallel patterns efficiently. And it is basically a SIMD pipeline, so you can take advantage of both SIMD parallelism and pipeline parallelism in the same unit. And then it is connected to other PCUs and to other PMUs through a switch-based network, which of course can be programmed to match the needs of the application. So if you look at the pattern memory unit, it is designed to provide the scratch pad memory and the communication, intermediate communication buffers between the pattern compute units, and it combines a configurable memory that can be configured to match both the parallelism and pipelining requirements of the compute units that it connects. And so you have these pieces together, and you are able to both manage both computation and communication, right? So performance in any parallel execution environment comes when you have the right balance between the parallelism in your application and the communication between the different parallel components. And traditionally, if you look in most processor-based architectures, you can program the compute to your heart's content, but you can't really program the communication, right? So you can't orchestrate the communication on chip very efficiently. You are at the mercy of the memory hierarchy that's on the chip. Whereas in a reconfigurable data flow architecture, you can reconfigure the communication to match the needs of the application, and this can give you tremendous performance improvements, or it can allow you to do applications that you simply couldn't do with the conventional approach. And so to give you an example of what that looks like, here is a data flow graph that you might get out of a machine learning application, and you can lay this out on the reconfigurable data flow architecture such that you have the different kernels which are using different PCUs and PMUs to be implemented, and then the communication takes place very efficiently through the switch-based network. And the net result of doing this is you get very efficient data flow execution that maximizes the compute and bandwidth and minimizes the memory bandwidth, right? And so one of the reasons that you can have very efficient use of the memory bandwidth is you aren't constantly moving data back and forth to the off-chip memory. You are communicating very efficiently through the on-chip network, and you get very efficient communication that way, right? So the first implementation of a reconfigurable data architecture is by SambaNova is the Cardinal SN10. So we call this a reconfigurable data flow unit, and this is the first one. It's a TSMC chip designed in 7 nanometer, which of course is basically the most recent process. It's got 40 billion transistors, and would you believe it, 50 kilometers of wire, right? So lots of connections between the different components. Hundreds of teraflops capability, and hundreds of megabytes of memory on chip, and then direct interfaces to terabytes of memory off chip. And so this is going to give you the capability of being able to train very large models. However, even though we've got a high peak teraflops, as I said, it's really about the efficiency with which you can use those teraflops. And the key to doing that is this data flow execution technique that uses the computation very efficiently, such that you get a lot higher than 6% or 20% efficiency, because that is what is going to give you the ultimate performance that leads to lower training times and more efficient inference. So if you look at the trade-off between programmability and efficiency, the reconfigurable data flow unit approach allows you to break out of the traditional programmability and efficiency trade-off curve that you see with conventional architectures. So if you kind of look up the x-axis, we kind of think of that as programmability, which is the time it takes you to kind of change the nature of your device. And so in a fixed ASIC, of course, it's infinite because you can't reprogram it. And in an instruction-based technique, you can do it, every few nanoseconds. And in this data flow approach, allows you to get efficiencies in terms of performance per watt much closer to ASICs with programmability and reprogramming time much closer to an instruction set-based approach. And so basically, you get the best of both worlds here, which is important if we want to enable both a flexible substrate that gives you very high efficiency that you need to keep the performance improvements for software 2.0 going. So if you think about the data science pipeline and training models for deployment, right? They typically go through these 3 steps where you start with what we call de novo training. You build a model up from the ground up, and you do a lot of experimentation. And RDU techniques with its very flexible substrate can do this. Then when you get a base model that you like, you might want to tune it and optimize it for a specific situation, right? And so the RDU, of course, since it has training capability, can do this. And then once you deploy it, you might again want to tune for the specific use cases, and the RDU does very efficient, batch 1 inference, but also can do training at the same time. So how about before you actually, train on your data, you might do some sort of data preparation and pre-processing that might involve interface to databases and data repositories. And so the question is sort of, can you extend this RDU idea to the sorts of things that one does in a database and make that efficient? And that's some of the things we're looking at Stanford. So this idea of accelerating machine learning on relational data, right? So imagine that you've got an database machine learning capability. Then you could execute a query like this, where you aggregate some tables, you join tables together, and then you train on the data that gets generated from this. And this would give you a unified, reconfigurable data analytics accelerator that could, both do things that are traditionally thought of as computational intensive ML, but could also allow you to accelerate SQL and data analytics sorts of things. And this will give you a much more flexible and interactive capability for developing new models. So what would be required would be to kind of augment the sorts of parallel patterns that are supported in an RDU. And so I've already talked about map and reduce and filter, but you might also want to be able to partition your tables. You would want to be able to sort your tables. You want to be able to execute group by, and of course, no database is complete without join, and so you want that sort of capability. And so the question is, can you add capability for these sorts of patterns without compromising the performance of the patterns that we already do very efficiently? And so the idea is by adding a little more hardware to the pattern compute units, to the PCU, you can actually achieve that. And the net result is that you can run a number of different queries very efficiently. In order to kind of see what sorts of improvements you can get, this is the comparison of Gorgon, which is this enhanced RDU to support relational sorts of operations, compared to Apache Madlib on a number of different kernels that combine machine learning and relational operations. And so, of course, the Madlib is running on a conventional multi-core processor, and the performance improvements are tremendous, right? So ranging from 200 to 3,000, and also, commensurate with the performance improvements are energy efficiency improvements that are also dramatic. And so on average, you get kind of a 1,000x improvement by using these techniques. And so let me conclude by saying, as I said, if you think about these key trends in next generation accelerators, right? Said, multi-core approaches are running out of steam. John Hennessy, Turing Award winner, has been going around the country talking about the fact that, it's multi-core is over, and the future is domain-specific processors or domain-specific architectures. And so the RDU is an example of a domain-specific processor. And so it kind of allows us to continue the improvements that we've gotten from semiconductors going forward by using this idea of a reconfigurable substrate, which is optimized both for compute and communication. And we've shown that this sort of approach allows you to come up with a single piece of hardware that allows you to converge training and inference, and that allows you to do all sorts of things that push the training that you do all the way to the inference time, right? And so the key to enabling this is to be able to do large batch inference very efficiently, and also large batch training very efficiently, and also batch one inference efficiently at the same time. Then lastly, this general applicability of accelerators for software 2.0 going beyond traditional ML can be achieved by small additions to this basic concept of the RDU, and this allows you to build a unified data analytics accelerator that goes everywhere from SQL sorts of processing to graph analytics and everything in between, and allows you to put the data in one place and accelerate the whole pipeline in a very interactive fashion. Okay, so with that, I'll end. Thank you. Simon.
Thank you, Kunle. We have time for one question while Josh is setting up.
Yeah.
Okay, I guess I can use this one. So,
yeah.
Over here.
Yeah.
You talked a lot about single chip performance. Right here.
Okay, there we go.
Yeah.
I saw the mic over there, yeah.
You talked a lot about single chip performance, but you also threw up the slide that everyone's been really focused on showing, 10x growth per year in training workloads.
Right.
Single chip's not really going to put a dent in that.
Well, you've got to have an efficient single chip, right? And then you build on that.
So what about the ability of your architecture to scale
Absolutely,
to
it can scale out.
thousands or tens of thousands and make all of our cloud service provider friends happy?
No, so I focus on the chip, and we'll say more about the chip going forward, and it has to be scalable. If you want to do large training exercises, you need to be able to handle multi-terabyte size, parameter models, and we have that capability.
Thanks, Kunle. Let's thank him one more time.